Now, I did not change my name during the break. It's Sirisha was my PhD supervisor many years ago, and Sirisha and I, with a few others, we've delivered a few workshops on data analytics. He has some really nice slides. I just asked him yesterday if I can use some of his slides, and he said, "Yeah, go ahead and use anything you want." But there are lots of slides. I'm happy to share them with you. I'm not going to go through all of his slides. There are a few that I thought I should touch upon during this workshop. I can share these slides, and then we will jump into data preprocessing, data visualization, and some basic clustering and classification algorithms. Is that okay? Yesterday morning, I talked about how big data, or generation of large volumes of data, computing power, and algorithmic advances have led to this revival of interest in artificial intelligence. And not only a revival of interest, but also have led to major breakthroughs in solving traditional computer science problems, right? And the presence of lots of data is what is called big data. Right? Big data is somewhat of a formal, it has a formal definition, and I wanted to present to you what that formal definition is. Big data typically have four primary features. One is it has a lot of volume, meaning lots of data. Velocity, meaning the data are collected at a really fast rate. Variety, meaning the data are of different forms: time series, categorical, text, video, images, etc. And veracity. Okay, so veracity is the accuracy of those data, right? So these four V's determine the big data. So volume, variety, velocity, and veracity. Veracity refers to uncertainty of the data. Right? So the data that has these four features is what is called big data. And one thing that I want to highlight is big data are not necessarily good data. Often, colleagues in the industry come to me and say, we have all this data, lots of data. Why can't you build some good models for us, right? And then we look at the data, we realize that the data are not good data. Right? It's big data, large volumes of data, but there's not enough information in the data to build meaningful models. That goes back to, I think somebody here asked, how do you get good data, or what is good data, right? That's a difficult question to answer, but unless the data are good, let me put that in quotes, you won't be able to build reliable models. Okay. So the point I'm trying to make here is in the industry, you will often find huge volumes of big data. Not all of that data are good data. Okay. Good data are data that have enough excitation in the data, that have the features that you're looking for through the modeling exercise. Okay. So before you start, in the next few days, 2-3 days, we're going to go through several steps that happen that are in the workflow of building machine learning models. One of the first things that you need to care about is the quality of data. Okay. There is routine industrial process data that's plentiful, meaning there are lots of this data. However, its usefulness for process and performance monitoring may be questionable. Not all of that data are useful. Data collection, archiving is basic infrastructure that is needed. You need to use correct compression tools. Ensure that any reconstructed data after compression is informative. I'm not sure if you know this. Did anyone here do an internship at an industrial plant, or have you had any work experience? Yeah. Did you use any databases? Where did you work? Can I ask you where? Sorry, yeah. Sorry, yeah. TCS. Okay. So what about you? Okay. And did they use databases? So where did they store their data? Sorry, what's that? Okay. Right, right. Right, right, okay. And did you want to say something? Right, right. So industrial databases, there are specific industrial databases. They're made by Honeywell. There's a company called OSI Soft, Aspen Tech, lots of companies. They make industrial databases. And when you store data, you often compress the data because if you're collecting data every second, you're likely to fill up the space on your computers very fast, right, or on your servers. So they compress the data. They only store data when the variable changes by a certain amount, right? Otherwise, they don't save. That's what the compression is. Now, when you're collecting data, you can lose information if you don't compress the data properly. So as an example, so let me see if I can. So let's say I'm measuring some temperature, and it varies ever so slightly here, and then there are big jumps, and then it just changes slightly, right? So when you compress the data, you don't you only save one value for all of the data, and then you save more values over here, and then you save just one value for that data. So that way, you are minimizing the amount of data. You're reducing the space, memory space you need to save this data, right? Now you can imagine that you're collecting thousands of these variables almost every second. You're accumulating massive volumes of data. But a lot of that is really not needed. If your variable is not moving, you can just save one value, right? Or one measurement instead of saving all of those measurements. So the point that is being made there is that you have to use the correct compression tools. If you, instead of choosing one value for this, you choose one value for this entire segment of measurements, then you're going to miss this feature in the data, right? So you have to be very careful in how you compress the data. And then once you compress the data, so instead of, in this case, for instance, you pick one value here, and you pick a few values here, and then you pick one value here. This is what you store. Okay, so you store that. I'm not sure, am I in your way? I mean, hopefully you can see it. So this is what you store. Then when you're performing analysis on this data, you have to reconstruct this original data set. Right? So, and that has to be done carefully. So when if you're working with industries and you get some data, you have to first ask them if there was any compression that was done on the data. If so, you need to know what sort of compression was done so that you can reconstruct the data appropriately. If you don't, if they have not used the compression properly, or if you don't reconstruct the data properly, then you're likely to lose some important features in the data. And if you don't have those, then your models are not going to be good. Right? And then obtain measures of quality, data quality or segment, partition data, and use segments that have the necessary information. Okay. So what do I mean by that? So if you have, again, I'm going to use some variable, let's say, let's call it y, and it's changing like that. And then there are sections where it goes up and down. There's quite a bit of excitation in the variable, then you don't want to use this segment of the data to build your models because there's not enough information there, right? No information there, or barely any information. Whereas there's a lot more information here, so you want to be careful in picking the right segment or partition of your data to build models. Make sure your data set has enough information in it. And then make sure that the data are well reconciled. Have you heard of data reconciliation? Often industries have redundant sensors in them. So, for instance, you have a pipe. You may have more than one flow rate, flow meter, more than one flow meter. If you have more than one flow meter, those two measurements have to reconcile, right? If there's no leak in the pipe, they have to measure more or less the same value. So that's called data reconciliation. So if you have redundant sensors, redundant measurements, make sure they all reconcile and there are no discrepancies. And of course, you have to pre-process your data by deleting and replacing outliers. There are several challenges with industrial data. There are various reasons why you want to pre-process your data. For instance, there are often outliers. What are outliers? Outliers are measurements that at least measurements that don't belong to your measurement, right? Whatever that variable is. So let's say you expect this variable to say in a certain range, an upper bound and a lower bound, and you suddenly get a measurement over there, then that is likely an outlier, not an artifact of your process, right? Then you have to identify all of those and replace them. So you can remove this and perhaps use linear interpolation here, find a corresponding data point that stays within the bounds in which that variable is expected to stay. So those are outliers. There are a wide range of standard methods for not only identifying outliers, but also for removing them and replacing them. You will often don't have to do this manually. You just have to, I'm sure in Python, there are tools to identify these outliers and automatically remove them. Yeah. Right. Yeah, so I think, there's a subtle difference between what I'm saying and what you're saying. When I say outlier, it is a measurement that is unlikely to have come from your process. Okay? In that example, they're not quite outliers, they're abnormal events. There's nothing wrong with the sensing. There is nothing wrong with the measurements I've collected. My sensors are working fine, the measurements seem reasonable within limits. But the product that I made in that particular batch is not of high quality, so I can't use it, right? But it's not really an outlier in the measurement. An outlier in the measurement is a measurement that couldn't have come from a real process. Okay, so let's be a bit more specific here. Let's take an example. Say, you're filling a tank and you are measuring the level. Okay, and there is a level sensor here. I'm measuring the level, and then I'm plotting the level. And at some point, the sensor fails, say for a second or two, and it reads nothing, Okay, so or you get a very low value here. And then the sensor starts functioning properly. Maybe there's a loose connection or whatever, right? Now these are clearly outliers. Right? It's a big, and you can, for instance, check if there is a valve here, and say there's a flow meter here. You're measuring the flow rates, you can measure the flow rate. Let's say you don't see any abnormality here, you haven't changed this, but your level transmitter shows this, right? Then you know that these are not the real measurements from your level sensor, because it's just physically not possible for your level to have gone down like that and come back up while you've not made any changes to the inlet flow rate or to the exit flow rate. Right? So those are outliers. So we want to find those outliers that don't represent the true behavior of your system. So let's take another example where they are not an outlier. So I'm going to take the same system, but I'll do something slightly different. Okay, so let's say I notice this. Okay. Now I don't want to immediately conclude that these are outliers, because if I had also noticed a change in the valve position, okay, I open the valve up and I see the level going up, and then I closed it and the level comes back down, right? So then that's not an outlier. That's a true representation of the process. So outliers are measurements that don't reflect the true behavior of a process. And often outliers are just way off where your measurements are expected to be, and they appear and then disappear rapidly, right? So inherently, some of these systems, they have an inherent time constant. So the level, for instance, cannot do this. It cannot go like this and then come back. Right? That doesn't happen because it has an inherent inertia time constant. It never goes up that fast or comes down that fast. So that particular data point or data points here must be outliers. Right? Okay. So data often have outliers, and sometimes data also have missing data. Right? If you have an outlier, you can identify it. In this case, for instance, you have these outliers. Once you identify these outliers, you replace them with new data points here. Okay. I'm not going to delve into various algorithms. It will take us more than 4 days to do that. But in Python, you'll find a variety of tools, algorithms to not only identify outliers, but also to replace them with appropriate data points. So outliers is a problem. And then missing data. Missing data is also very, very common in industrial data sets. So for instance, let's say a sensor fails and is not reading anything. Then you have missing data. Or maybe there was some sort of a communication failure. Or sometimes sensors read NAN. Okay. So T and some variable Y. So you have data coming in like this, and then suddenly you find that there's no data, and then it comes back up. Okay. Your sensor is reading this NAN for whatever reason. Then that's considered missing data. Then you have to fill the missing data. It's called imputation. You impute data here. So you look at this. There are different ways of doing this. So for instance, you can fill it with say a quadratic function or some other higher order function. You can also have bad data. It's not just outliers or missing data, but you can have wrong data, things that are not something that you're expecting. Okay, so you have to correct, or sometimes bad data is simply not usable, and you throw it away. The rest of the data, you remove your outliers, fill in for missing data, and any other features in the data that you want to correct all of those, then that becomes your good data. Okay. Okay, so once you have good data, you have to sometimes do filtering or smoothing. Do you know what filtering is or smoothing? Filtering. Let's not get into technical details. The filtering is it's about removing the noise, right? So you filter the data based on sorry, yeah. You can use thresholds. There are different ways of filtering data. Smoothing is you need to filter or smooth because when you have measurements, there is associated noise, right? So let me see if I can explain this intuitively. There are three things, statistically, there are three things you can do with the data: prediction, filtering, and smoothing. I'm going to do a little bit of hand waving, so it's not very robust theoretically, but it sort of helps you understand the difference between prediction, filtering, and smoothing. Time y, and let's say I have some data of y, and my current time, let's call it t star. Okay, so that's the current time. I have all of these measurements known. These are known measurements. Okay. Using these known measurements, if I'm predicting, let's call predictions. If I'm guessing what y is going to be after t star, okay, given all the information up to t star minus 1, I have all the y's from y0 to yt minus 1. I want to use this information to predict y at t star. Okay, and beyond. I can also predict y at t star plus 1 and so on. So these are called predictions. These are predictions. Okay. I can also, so I have, let's say, once I have the measurement, the real measurement at yt star, okay, I can use all the information that I have previously to estimate the true value of yt star. Okay, so what do I mean by that? This is my measurement, right? So sorry, I put the star at the wrong place. Yt star is my measurement. But because all sensors have some noise, there is some true yt star that I don't know. You add some noise to it, then you get your real measurement. This is your measurement. Okay? This is your measurement. This is the true value of your variable. This is some noise. All the measurements you're getting are these noisy measurements. But if you want to know the true value of your measurement, you have to figure out a way to eliminate this noise. Right? There is information about that noise in the known measurements that you have. You've measured this several times in the past. Therefore, information about this noise must be embedded in those measurements. So you can use that information to come up with an estimate of this y bar t star, a better estimate than the measurement. And that is what is called filtered y. Okay, so this is filtered measurement. Okay, so you can improve it. Now, you can do something else that's interesting. Let's say you not only have measurements up to yt minus 1, you continue to measure all the way up to y some capital T into the future. Okay. Now, I can again estimate this true y bar T star using not only the past values of y's, but also the future values of y's. Right? Does it make sense? I mean, it can be a little confusing, so I'm happy to pause. You have this measurement here. This is our measurement of interest. That's our measurement of interest. Now, if I only have measurements up to t minus 1, then this is going to be a prediction because you haven't done it yet. Or if you're doing t plus 1, that's a prediction, something in the future. Okay, so there are optimal ways of calculating those predictions. The other problem, so that's the prediction problem. The other problem is at t star, I have the measurement, yt star. Okay, I have the measurement. But I know that measurement is corrupted with noise. And the question I'm asking is, if I have all of these past values of y, they must have information about the noise, the type of noise that my sensor is generating, right? Then can I use all of those measurements to come up with a really good estimate of this y bar t star, right? And it turns out that there's an optimal way of doing that. And when you do that by using all the past values of y, up to yt star, then you have what is called a filtered measurement. Okay, so you're using all values of y up to the current time, t star. Okay, then you have formal mathematical way of writing this is expected value of y t star, right, given all your measurements up to yt. Right. So that's the filter. The third problem, or a third way of estimating this unknown y bar t star, is to not only use past values of y, but also future values of y. So let's say you finish your experiment. You have all values of y from 0 times 0 to time capital T, and you want to go back and get a better estimate of this. Okay, now you not only have the past values, but also the future values. If you include all of those measurements, you'll get, hopefully, a far better estimate of epsilon, the noise, and therefore, a better estimate of this true value of this measurement, right? So that's called smoothing. Okay, so when you do predictions, you use past values of y to get an estimate of y at time t. When you do filtering, you use all the values up to time t. When you use smoothing, you use past values as well as future values to get an estimate of this kind of thing. Okay, so the idea is very simple. You want to get the best estimate of noise. Using both past and future measurements gives you a better estimate. That's the logic. That's called smoothing. So once you have the data, you might want to smooth and filter the data. Then you have to process the data. You can build models, soft sensors, do causality analysis, and a variety of other things. Some of these boxes here are not entirely relevant to what we're doing in this course, but I think you have to be able to do or execute all the steps up to filtering or smoothing before you feed your data to machine learning algorithms. All right. There are a couple of simple examples, 3 examples. I can probably skip these examples and dive into. I have more examples coming up, so I will just skip these examples here and dive into my lecture. Oops. Sorry, some of these slides were originally prepared in LaTeX a few years ago, and I forgot to change the date. I will fix the date and give these slides to you. But I could not find the appropriate LaTeX file. These slides, we've been doing these data analytics workshops for several years now. These slides were prepared by Eating Sai. He was a PhD student of mine. Lee Rippon, also a PhD student. Aditya Tulsian, also a PhD student. We've given many of these talks at different conferences. So I've used some of those slides and a few new slides, etc. So I apologize for the date on the slide here. This particular version was given at NUS Singapore in 2019, just before the pandemic. All right. Okay, so the objectives, we want to introduce you to some machine learning algorithms, software tools, and provide practical applications in the context of process industries. I don't think I need to go through these the motivations. Hopefully, over the last 1.5 days, I've motivated you enough. Okay, some notation moving forward. This is standard in machine learning literature. If you have our notation is based on Ian Goodfellow's book, which I alluded to yesterday. Scalars are in lowercase, plain font A. Vectors are in bold font, A there. Matrices are in uppercase, bold font. Random variables, I'm going to use lowercase, plain type face, X. A particular value of a random variable is denoted by a lowercase letter in script, X. Probability mass function or probability density function of a discrete random variable is denoted by this capital P. And then a probability density function for a continuous random variable is denoted by lowercase p. How good is your background in statistics and probabilities? I think most engineering students take a course in the first year, right? Or maybe second year. So have you all taken a course on statistics and probability? So you know what random variables are, right? Can somebody tell me the difference between this X and this X? This one?
Yes, yes. That can take a range of values.
Right.
And this, that is X, that is a specific value.
Right. That's right. Yeah. So random variables, when you talk about a random variable, and when you're treating that as a variable, it doesn't have a unique specific value assigned to it, right? So that's when you use this X. But once a realization of that variable has occurred, then you have a specific value. So if you think about some of these examples, before I measure YT star, it's a random variable because I don't know it, right? But once I measure it, then I have a value for YT star. Right? So that's the difference. All right. So some of these are very intuitive, and you may have already used this notation. We're going to use capital X to denote input data matrix. It typically has real values with small n rows. Those are the number of data points. And then the columns correspond to the number of features in your input data matrix. And the number of features are denoted by dx. The output is a vector y in Rn. It doesn't have to be. It can also be a matrix, in which case we'll replace this dx with dy. And these are outputs are the labels, right? Okay. And for supervised learning, output data y contains values of a particular label or target that we're trying to optimize. A particular value yi corresponds, yi is a label of the corresponding row of features xi. Okay. The input data x refers to the design matrix, and it contains, as I mentioned earlier, dx different rows as columns, and n values of these features as rows. Okay, so there are different ways of writing this x matrix as rows or as columns. Okay. So each of these columns correspond to different features. In this case, we have dx features and n rows. Each row corresponds to one measurement of those features. All right. Now, once you collect this data, once you prepare your data matrix, it's very, very important to standardize or normalize your data. Okay. So if you don't do that, you can run into significant problems with machine learning tools. For instance, one common approach to data scaling is to remove the means from all of your features and divide them by the standard deviation of that feature. So let me see if I can draw this. Okay, so let's say your variable, the true variable, this is your true variable, right? You first remove the mean. So when you remove the mean, so this is t and y, it's going to be here, right? The same pattern. Sorry, it's probably not as good as that. So you're removing the mean. This is the mean of this data. You remove it and bring it down to here. Therefore, the mean of the process data is 0. You not only do that, but you also normalize it by dividing it with the standard deviation. So when you divide it by the standard deviation, depending on what the standard deviation is, if it's greater than 1, then you're going to see something like this. New data set. It's going to be similar to this, but has smaller variance. Right? The goal there is to push the variance of the normalized data to 1. Okay? And why is this important? Let's say you have some variables that are of the order of 1,000, other variables that are of the order of 1, let's say. So an example would be, you have temperatures that are about 1,000 degrees Celsius, and maybe there is a concentration that is 0.5, right? And you're trying to build a model. When you're trying to build a model, what you will do is you will take your temperature, errors in temperature, let's call it E of t, and then you add it to errors in concentration, and you minimize these errors. When you build a model, that's what is typically done. Now, errors in temperature are going to be much larger than errors in concentration. If you have a typical optimizer and you don't weigh these two properly, your optimizer will focus entirely on this and minimize those errors and ignore these errors completely. Okay, so therefore, you'll end up with a model that's good for your temperatures but not for your concentration. You want to make sure that the the magnitude of different variables does not impact the optimizer or the performance of the model. That's why we wanted to standardize data. There's this, I'm sure you understand this, right? This is basically the mean. We use ij to represent different elements in the X matrix. I corresponds to the ith row, j corresponds to the jth column, and this is essentially the formula for standard deviation. As I mentioned, standardization ensures that regularization of W has a similar effect on each feature. Similarly, the scale of the label yi is often standardized such that it's on the same scale as the standardized features. So just like how we standardize inputs, we also might want to standardize the outputs. Remove their means, divide their values by the standard deviation. Okay. Now this, some of you probably know the difference between training, validation, and testing. Can anyone here explain to me the difference? Training, validation, and testing. What's the difference between? Yeah, go ahead. Okay. Uh-huh. Okay. Yeah. Right. Yeah, yeah. You know, sometimes in literature and in textbooks, perhaps, the distinction between validation and testing is not clearly explained. Okay. So I want to help you understand the differences between validation and testing and training. As you say, training is the first thing we do, right? So we have, let's say we have some data set. So we divide that into training data set, and then validation data set, and testing data set. Okay? We use training data set to build this model. Okay. But to build a model, we not only need the training data set, but we also need what are called hyperparameters. Okay. So what are hyperparameters? If you're building a neural network, the number of neurons that you want to use, number of layers you want to use, the activation functions you want to use, those are all hyperparameters. Those are choices you make prior to training your model. Right? You're not optimally choosing these parameters beforehand or through the training process. You fix them and then train the model. So you choose your hyperparameters, provide the training data, then you get a model. Okay. Now you want in order to test if this model is good enough, you don't want to use the same training data set. Right? Makes no sense because you've just trained it on the training data set. It is going to work really well on the training data set. So what you do then is take some validation data set. Validation data set. Validation data set is completely separate from the training data set. And then you check the performance of the model. So this, Some of those arrows probably don't make much sense, but you get the idea. Right? So you take that model, the same model, you take validation data, and then you check what the performance is. Okay. If you have a good model, it should perform well on the validation data as well. Right? So it may not perform as well as with the training data, but it should come close to it, close to the performance on training data. Now, if this performance is good, then you don't have to do anything, right? But if the performance is bad, if it's bad or if it's poor, then you go back and fix your hyperparameters. Okay, so if you, so let's say you're building a linear model or a polynomial model, you've used a quadratic model initially that did not work, then you try a fourth order or a third order model, et cetera. So you change your model structure, change the hyperparameters. And you repeat this loop until you're satisfied with the validation performance of your model. And when you're satisfied with the validation performance, when that is good, then you take that model and feed it the testing data. Okay. You want to keep training, validation, and testing data separate because the ultimate test of your model is in checking if it provides you with good performance with testing data, right? In this entire process here, your model has not seen the testing data, hasn't seen the testing data. It sees it only here, right? And that's why you want to keep this testing data separate from rest of the data. Training data, validation data, you repeat through that loop until your performance is good, and then you test it on the testing data. That's the standard framework under which machine learning models are built. Yeah.
So this validation set is mutually exclusive to the training set? Is it like that?
Yeah, they're not the same. Validation set is separate. Because if there are overlapping data points, then you might end up seeing deceptive performance from your model, right? So, if, for instance, if validation data is same as training data, then obviously your model is going to perform equally well with both data sets. And when there is overlap between those data sets, then that can give you wrong performance. Does make sense? Deceptive performance, I guess. So you've mentioned only training data set and testing data set, right?
And I was asking, training data set and validation set, are these two mutually exclusive?
Oh, sorry, validation and training. Yeah, they have to be. So training, validation, they're all separate. There is no overlap. Yeah. Typically, there's no overlap. I mean, you can have some overlap, but ideally, you should not have any overlap. You might have overlap if there's not enough data, right? If there's not enough data, then you might consider a little bit of overlap. But if you have enough data, ideally, you should have separate data sets. I think when I first asked you about the difference between training, testing, and validation, you've mentioned only training and testing, right? Not validation. That's partly because sometimes this step is not implemented, right? So you don't go and fine-tune your hyperparameters. If you don't have this step, then you only have training and validation or training and testing, let's say, right? There's no internal loop. But if you want to adjust your hyperparameters, then you have to go through this process. Okay, so input and output data are divided into training, validation, and testing sections. There are many heuristics for how these data are split. For instance, if you have data of the order of 100 to 10,000 data points, you might want to do 50% training, 25% validation, 25% testing, or 95 and 5. But if you have really large amounts of data, then you can do away with smaller training and validation data sets. There's some thumb rules, but generally, for large, my advice to you would be if you have a large, really massive data set, go with T10, 10. If you don't have enough data, then do 50, 25, 25. Right. Okay, so I think this slide explains the picture over there. Training, it's about mathematical mapping between input and output, known as models. Validation of each model formed during training to optimize given performance metric. Example, using k-fold cross-validation. I'll talk about that in a bit. Testing the ability of the model to generalize to new samples via performance metrics. The test set, you have to be very careful that it does not influence the choice of model structure, parameters, or hyperparameters in any way. Okay. Yeah. So sorry, in validation, you're not actually training. Yeah. Yeah, that's what I'm saying. So you're not training in the validation step, right? So you're only training in the first step. You get the parameters for the model. You use those models in the validation step. So the same model, same parameters. You're not estimating parameters again. You just take the same model, but test it on this new data set and check the performance of the model, right? So that's all. So training or optimization is only done in the training step. There's no optimization done in the validation step or in the testing step. Parameters are generated only in the training step. Those parameters, the same model is used in the validation step as well as the testing step. In the validation step, you you check the performance of the model against the validation data set. And if it's good, then you stop it, go to the testing step. If it's not good, you go back and tweak your hyperparameters, retrain the model, estimate new parameters, and pass them back to the validation step. That's how you repeat this process. Yes? Yeah, you could do that, yeah, 80-20. You will find that a lot of people don't do validation and testing. They just do validation or testing, no validation. That's okay if you don't want to change your hyperparameters. Okay? Yeah, in a sense. So because you don't want to use the same data set for validation and testing, because if you use the same data set, the data set that's used in validation step, the information in that is intuitively captured during training, right? Through that feedback loop. So what's the idea? I mean, why are we trying to separate the data into three sets? We're doing that because the true test of performance of a model is in assessing it against a previously unknown data set, previously not seen data set, right? So that's the true gold standard for testing models. the validation data set is something that the model has already seen, albeit indirectly, because based on the performance of the validation data set, you're going back and fine-tuning your hyperparameters, right? So in other words, indirectly, your training model includes information that's in the validation data set because of the feedback loop. So that's why you don't want any overlap between validation data set and the testing data set. Sometimes validation step is avoided. You just go to testing. And sorry, can you repeat your question? There's a microphone.
So we are hyper-tuning, we are changing the parameters once the performance in the validation is not good in our training data sets only. And then again, once we get the updated model, then we are using it for validation. Then how that validation is affecting our training process so that we need another testing data sets?
So you do testing only once. Right? So you don't do testing repeatedly. But you do training and validation repeatedly. Right? So the validation data set tells you whether the hyperparameters that you have right now are good or not, right? If your validation is bad, then you should go back and fix your hyperparameters. Right? So that's why you're going through those loops. But testing is only done once, after you're done with those iterations between training and validation. Sorry, can you repeat that question again? Oh, I see. So you're talking about K-fold validation, I think. Okay, yeah. I think I have a slide on K-fold validation. So sometimes what you have to do is there are different models, so say neural networks and something else and something else. And you want to compare their performance. Then you use something called K-fold validation, where you split your data set into K different pieces, and then you build models on each of those pieces. You split it into K different ways, and then you build models, multiple models, and then you take the average performance of all of those models. Now you repeat this exercise with different algorithms, different approaches, and find the approach that gives you the best average performance over K different data sets. I think I have a slide on that, so we'll delve deeper into K-fold validation. K-fold validation is a commonly used tool. Okay, let's see how much we have. 15 minutes more, and that's perfect timing because I can talk about bias and variance trade-off. Now, I think, knowing what I know right now, some of these slides are probably outdated. There have been some major advancements in our understanding of how bias and variance trade-off works. But I'll show you the plot here, and then on the board, I'll explain the changes in our understanding between bias and variance. Now, before I go into bias and variance, can I ask you if you have a good understanding of the difference between bias and variance of a model? Can somebody explain what is bias in a model? What's variance? Okay, so let me explain this with a very simple example. I will assume that there is a true system. I'm going to call it S0. Okay, a true underlying system. In practice, of course, we never know what this true system is, right? And the system behaves like this. My output y, t, is simply some alpha 0 plus some alpha 1 times the input plus some noise. Okay, this is the truth, ground truth that we will never know. Okay? Now, because we will never know when we are estimating a model, we might use a different structure. I'm going to call this S1, and my model is yt is equal to alpha 1 ut plus epsilon t. Okay, so because I never know what this is a very simple example. You probably have a more complex nonlinear system that you would never know, right? So because I don't know this, I assume when I'm building my model that this is what the model is. And from the data, yt and ut, I want to estimate alpha 1. Okay. Now, my estimate, you can use least squares to estimate alpha 1. So I'm going to get some alpha 1 hat. Okay. This is the estimate using the data, yt and ut. You use that to estimate this alpha hat 1. Now, for let's say we have we do multiple experiments. Okay, so I do my experiment 1. I collect data, n data points. Okay, and I get alpha 1 hat. I'm going to use 1 to denote experiment 1. And then I do experiment 2. I collect new data, yt to ut, also n data points. Now, am I going to get the same alpha 1 with the second experiment, or is it going to be different? Is this going to be alpha 1, 1, the same thing? Or, sorry? It'll change, right? It's not going to be the same because you've conducted a new experiment, there is noise in the data, you may have seen different noise, so when you repeat the experiment, you're going to get a different alpha 1 hat. Okay. Now you can imagine repeating these experiments many number of times. Okay? And take all of these alphas, estimates of alpha 1s, and find their variance of alpha 1 hat. Okay. So this is going to be some value. That is what is called the variance of your model, okay, or the variance of the parameters. This represents the variance of your parameter, alpha 1. That's the variance error in the model. Ideally, you want this variance error to be 0, right, or very small. But because of the noise in your system, and when you do multiple experiments, there is going to be a variance that you cannot get rid of in your alpha 1. You can only do finite number of experiments, therefore, this is going to have a variance that cannot be driven to 0, exactly 0. Okay. So that's what is called this is called the variance error. Okay, anytime you estimate a model parameter, there is going to be this variance error. And you can show that this variance actually is proportional to small n over capital N, where small n is the number of parameters. And capital N is the total number of data points. Okay. So what it is if, now in this case I have one parameter. If I add one more parameter, then the variance for fixed data, fixed number of data points will increase. If you add more parameters, the variance is going to keep increasing. On the other hand, if I fix the number of parameters and increase the data, in other words, I do more experiments, then the variance is going to decrease. Okay. So let's see if we can plot this with that understanding of variance. I want to plot number of parameters on x-axis and variance of those parameters on the y-axis for a fixed amount of data, let's say. Okay, so I'm fixing my n. What should this look like? Yeah, so it's when you have a small number of parameters, then you have low variance, and as you increase the number of parameters, variance should go up. I want to leave some space on the right-hand side, so I'm going to redraw this. Okay, so it goes like that. Now, what is bias? Does anyone know what bias is in this example? So bias is a result of the structural mismatch between the truth and the model that you assume. Okay. So the bias error is, so you've assumed you're only covering this part of the true model, right? No matter what value of alpha 1 you pick, you're never going to account for this constant. There is this structural mismatch that cannot be eliminated by any value of alpha 1, right? So that is the bias error. Okay. Variance errors you can reduce variance error by increasing the number of data points, but you can't reduce bias errors by increasing the number of data points because it's inherent in the choice of your model. There's just no way you can get this error, or you can eliminate that error, right? So that's called bias. So the bias in this case is the bias error is alpha 0. Now, what do you think the bias error graph would look like here? What would that be? As the number of parameters increase, what do you think happens to the bias error? Yeah, so when you have fewer parameters, if you have 0 parameters, your bias error is going to be even greater. But as you start increasing, if you add 2 parameters, then your bias error will likely go to be very small. And as you increase the number of parameters, it drops further, right? So it goes like that, okay, roughly. The mean squared error is the sum of bias and variance errors. That's called mean squared error. Now let's add these 2 errors and get mean squared error. So you add these 2 errors, then you're going to get a curve like this, mean squared error. Okay? Now, many standard statistical textbooks, I think I have it here. Here's validation. Many standard textbooks on statistics will show you this, right? So bias and variance errors and finding the right trade-off. And for many decades, we've been teaching students that you should build parsimonious models, meaning models that are complex enough. The complexity of models increases with the number of parameters. You want to build models that are complex enough, but give you the best mean squared error. So if you look at this curve, you should be building a model with this many parameters. That's the sweet spot because you have the best combination of bias and variance errors. Okay. But it turns out that deep learning models have billions and maybe even trillions of parameters, right? In other words, deep learning models are over here, right? But they don't fall on this MSE curve. And that was a major puzzle for statisticians and mathematicians when deep learning started becoming popular. You know, these models have millions, trillions of parameters, but they also have very small errors, mean squared error. Right? They don't. How come they are not following this curve? Right? It was found about 5 or 6 years ago that there is a point over here beyond which the MSE actually drops again. Okay, and we did not know this I find it very fascinating because we didn't know that MSE drops after you cross a certain threshold of parameters. This is called double descent. If you search double descent on Google, you'll find lots of videos on why this happens. Okay, I think we're at time. This is a good place to pause for today. I'm happy to take questions. Yeah. Yeah. Sorry, the variance is also reducing. Yeah. So that, this is a fascinating phenomena for me because, I grew up, my training was all about build simple models. It's called the principle of parsimony. Don't build complex models. And this, this is going to be the simple model that gives you the best performance, right, if you look at it. But then these deep learning models are much more complex, provide far better performance. Yeah.
While solving a problem, we follow all these steps for reaching the result and come up with some parameters. So should I always check what is the number of parameters? Should I go for this curve? Then I should proceed, or all these things are taken care of already in the algorithm.
Right. Yeah. I would say even today you can probably stick to this for simpler models. If you have to be here, you have to use something like deep learning, right, with millions of parameters. Otherwise, you will not reach there. But you could end up somewhere here, which is not good, right? You have a better optimal solution here. To get there, you have to use massive amounts of parameters. All right. Okay. So hopefully there were some good takeaways for today. I have, as I said, tomorrow I'll show you some Python notebooks. If you have laptops, please bring them tomorrow. And if you don't have a Google account, please set up a Google account. Thank you. Enjoy your lunch. Yeah. We'll go through those. K-means all the. Tomorrow, I'm hoping to finish clustering and classifications. Yeah, with Python notebook. We'll do a little bit of data pre-processing as well, and then we'll do dimensionality reduction. On tomorrow is Wednesday, right? I think that on Wednesday. On Thursday, we'll do dimensionality reduction. On Friday, reinforcement learning.
Tomorrow we are starting at 8, 9.
Are we starting at 9:30? Okay, Surendra told me, but I didn't want to trouble you, but I'm happy to, come in a bit early for 9:30.
If it is finalized, then we can adjust.
Yeah. Just follow whatever instructions you receive from Surendra. Yes. Okay.